So let's look at interrupts with a lot more detail. Remember that interrupts are an asynchronous signal. So an interrupt request, IRQ, is a signal that occurs that we want to handle with some kind of function. We want some process to execute when this when this asynchronous signal, this IRQ, occurs. What this really does for us is it allows us to set up the hardware to monitor for certain conditions that will allow us to execute functionality later on, right? So we don't have to poll for it. We don't have to waste CPU cycles on it. The hardware itself is the part that's checking, and we don't have to do anything. We don't have to worry about it. So here's an example. We've got a deaf baker, and he's making 2 loaves of bread in his ovens. So this deaf baker would like to set an alarm when his bread is done, but he can't hear it, right? And in reality, there's like all kinds of fancy stuff that allow deaf people to handle this sort of thing. But let's just take this example on its face value. So this blind baker, basically what he has to do is he has to run between his ovens and keep checking to see if which one is done. And if one of them is done, then he has to take it out of the oven and start slicing it. But what might happen is that while he's slicing the bread, the other bread might burn. It might do something bad for him, right? So while he's in process and not paying attention to something else, another signal has occurred and it has caused a terrible tragedy, which is burned bread. And we definitely don't want that, right? So what the blind baker does is he goes and gets a new system where he has a little pager, and the ovens will notify him. They will buzz him when they're done themselves, right? So he's set up a hardware system, a system where he's got some smart ovens, and they actually give him a little buzz whenever they're done. So rather than having to run between the ovens and check, he can go and do something else. He can relax on the beach, and there's no problem at all. Right, so when the first bread is done, it buzzes him. He goes to slice it, and while he's slicing, if he gets another signal, it buzzes again, and he can go and handle that one temporarily, and then slice it later, so that there's plenty of bread, and he hasn't wasted anything. Right, so that's the basic concept. And in this case, the interrupts are his pager system. It's a hardware system that allows him to be notified anytime something occurs, and we can associate some behavior with that and handle it accordingly. So the whole idea here is that we have these time critical events that we need to deal with, and these interrupts allow us to handle that without wasting CPU cycles. It's a really simple form of multitasking that allows us to do multiple things at once, and it's through a method called time slicing. So we don't actually have multiple processors, we just have something that allows us to pause one thread of execution and then go and do something else and come back to it later. So if we do that fast enough, it looks like we're doing 2 things at the same time, which is basically what multitasking is. So let's talk about what happens during an interrupt. All of the interrupt sources on our machines are hardwired, and they can be associated with some external signal like we have here on the left, or we have some timer, some internal signal or peripheral, right? So these interrupt sources are built into the system. Because this is a hardware system, the interrupt sources are specified by the processor architecture. So when a particular interrupt signal is triggered, it's associated with a interrupt vector, or a pointer. Basically, it's a function pointer to a behavior that we want to execute when that interrupt occurs. So, and these are all stored in what's called a vector table, or an interrupt vector table. And it's basically a big table, an array of function pointers that allow us that each slot is associated with a specific interrupt request number. So the timer might have interrupt number 1, and the external signal might have interrupt number 2. All we have to do is fill in the appropriate function slot with whatever we want to associate with that interrupt request. In this case, we've got remove bread when the timer runs down, and measure the temperature when some external signal occurs, like we hit a button or something like that. So Let's look at what happens during a real interrupt. So here I've got a main function that is just really simple. This is the relax mode for our blind or deaf baker. And he's got sift mojito, observe ocean, apply sunscreen. These are all the tasks he's doing when he's not actively like making bread or anything like that. Say we hit play and the deaf baker is off to the beach and he's just handling things and not worrying about anything at all, right? He's sipping his mojito and looking at the ocean and he's happy. So he's sitting at the beach and he's having a great time. Now, let's say one of the timers go off and that triggers an interrupt request. And the first thing that happens is that the execution is paused. The guy our deaf baker has to get off of the beach and stop whatever it was that he was doing. Everything that he needs to know about what he was doing, he saves. He basically bookmarks. So he bookmarks whatever he needs to do by putting it on the stack, right? Basically, he saves his place in the current thread of execution, and that lets him remember where to come back to after he's done servicing the interrupt request. The next thing he does is look up his slot, use the interrupt request number to figure out what function he needs to run in the interrupt vector table. In this case, it's directly associated. Slot number 1 is interrupt request number 1. So he has to execute the remove bread function. He executes that. Then when it returns, we can look up where we left off in the main thread and start executing from there, and everything goes back to normal. So the basic process for handling an interrupt is that an interrupt service request or interrupt is requested during normal execution, and we pause execution by saving the program counter and the current status register onto the stack. We make sure we bookmark it. Then we look up the interrupt service routine based on the interrupt request number. We execute the interrupt service routine. Then we restore the program counter and status registers back on from the stack, and we basically look up our bookmark and figure out where we left off. Then we resume normal execution of our program.